Thank you so much. All right, hello everyone. Last stretch of SwiftTO. Hopefully you got to stretch your legs. I'd love to hear a big round of applause for Kyle, the organizers, the venue staff. Please give it up. It's been great. My name is JP. Today I want to talk about some of the Swift patterns that I've seen in projects over the years that aren't exactly the widespread kind of patterns that you see in every project. They're not exactly the best practices necessarily, but they're interesting enough that I thought it was worth highlighting a few of them today. So let's take a look at what some of them might look like. First of all, show of hands, who's ever written a comment that looks something like this? Yeah? Okay. Now, keep your hand up if that comment outlived your time on the code base. Yeah. So it may be a mark of shame. Your colleagues may have scolded you. But today we're here to celebrate you. This is a moment of highlighting and of recognition. And to do that, we'll use a well-known superhero blockbuster movie from 2021. You superhero fans surely have seen this one. It's called The French Dispatch. Yes, I have some French Dispatch fans in the audience. Fantastic. Now, for those of you who have not seen this movie, I'll introduce you to our cast. So we have Mr. Timothée Chalamet, who will be playing the role of Generics. We have Wes Anderson, who will be showing us some fun things that we can do with DLSim. Tilda Swinton, who will highlight some fun refactoring tricks. And of course, the incomparable Bill Murray, who will be showing us what we can do for testing. So it's a bit of a grab bag cast, but we love each character for its own quirky reasons. First off, Timothée Chalamet, who will walk us through some fun things that we can do with generics. Who has fun with generics? Everyone has fun with generics. Yes, generics are great. What are some of the fun things we can build with generics? Here's one. We can build generics trampolines. Applause. Yes, trampolines. Everyone loves trampolines. What's a generic trampoline, you might say? This is a fun trick that you can use whenever you have this external API. It's defined in some dependency somewhere you're pulling in. You don't control this. And say you're told, Dev, we need a way to monkey patch this API so that every time someone creates one of these external types, we can run our own custom code. Maybe you're doing some telemetry, some analytics. Maybe you just want to do whatever you want to do whenever you're creating one of these types. Or really, this doesn't have to be an initializer. It can be any sort of external API. All right? And your response, of course, is this isn't Objective-C. You can't swizzle this, right? So how do you do that? Well, the answer is you can build a trampoline. These are fun. So you can use this pattern whenever you can constrain an API with a more constrained generic type. So for example, in this case, we are constraining the initializer on equatable values, which is more constrained than what was defined upstream in the external dependency, which is no generic constraint. That means that whenever I'm passing in something that conforms to this protocol, something that is equatable, it's going to hit my definition first. From there, we can build a little trampoline that is less specialized than the thing that we are calling into to finally bump it out to the external call. Let's take it step by step and see what this looks like. First off, say you're creating this external type. You're passing in one. That's equatable. That means that the compiler knows, instead of calling out to the external initializer, there's a more specific match in the code that you've written. And so this is the first thing that you call. That's the override. From there, you'll see that we are calling out to the trampoline initializer. Right? That trampoline initializer has the same level of generic constraints as the thing that we're ultimately calling into, but it has a different initializer signature, right? It has the explicit trampoline label there in the initializer, which means that we can explicitly go from our generic initializer, the specialized one, to this one, which matches the same one as defined in the external library. And then finally, by calling in it here, we are calling out to the less generic one, right? So this way, anytime you're creating something with this external type, you're going through this trampoline, right? So that's kind of fun. Why would you ever want to do this? Well, this way, you can add in your customization, your overrides, your logging, your analytics, your instrumentation, whatever you want to be doing here, without having to change everywhere in your code base where you're using this external API. OK, that's kind of nice, sure. You can also just keep using those external APIs as you've always had. That means if you're referring to its official documentation, you're using that. Everything seems like you're just using everything as it's designed, but there's a few reasons why you might not want to do this. It's kind of really implicit and sneaky. When you're reading through the code, you might think that you're just calling out to the external thing, but really you're hooked in there. And there's nothing happening dynamically at runtime here. You're not swizzling anything, but still you're sort of hinting to the compiler that you want to go through your own trampoline. Your colleagues might not like you, because at this point, if they're trying to understand the code, there's some sneaky stuff happening here. And whenever the external API changes, well, you need to make sure that you're matching its new type signatures. So a few reasons why you might want to think twice about using that. Let's move on to the next pattern. What other fun things can we do with generics? You can silence deprecation warnings. This is occasionally helpful whenever, say, there's a new version of Xcode, a new version of iOS, or whatever platform you're targeting. Although generics isn't quite the tool we're using to solve this problem, it's more specifically about protocols. So one of the things that you used to be able to do when we were writing Objective-C and the C-based languages is that you could tell Clang to ignore certain types of warnings, certain type of deprecations, and that, if you're using warnings as errors in your project, can help you extend your runway a little bit, where you can maybe mark a few of the cases where maybe you need to rethink things, you're going to take a little bit more time to get to migrating that, while still being able to compile cleanly with no warnings. So how do you do this with Swift? Well, let's say that you have this API, this person can attend a film festival, and that's a really useful functionality that you want to keep. But in the next version of this film festival SDK, it's marked as deprecated, and maybe there's no good replacement for it, but you still need to call it while you figure out a good migration strategy. So what can you do? You can define this protocol that matches the same type of type signature, and by making your type with the deprecated function conform to it, you can then call that via the protocol. And that way, the compiler doesn't quite know right away that you're using a deprecated method, because you sort of have this level of indirection here. There's a few reasons why you might want to do this. You can keep your code base warning free. Gives you a little bit of extra time to migrate to whatever you want to move towards that's not deprecated. And sometimes there just isn't a good non-deprecated equivalent whenever something's deprecated. Now, why would you not want to do this? Well, first of all, you're really just sweeping your warnings under the rug. They're not gone. You're just sort of hiding them from the compiler a little bit. And it might surprise you whenever that API is just like fully gone, and you might be caught off guard there. So you're just putting a blindfold on your compiler. The warning isn't gone. It's just not seeing it at that point. Let's move on to our second cast member, Wes Anderson. And Wes is going to show us some fun things we can do with DLSim. And this is the face that I make whenever I find code that's using DLSim. I don't know if that's a good face or a bad face, but I'll let you decide. It's a little bit of both, I think. DLSim is this powerful API. It allows you to access the internals of your dependencies. And this is sometimes helpful whenever you want to enhance or otherwise change or fix your dependencies. And in fact, the Swift concurrency system has an internal hook that it doesn't expose in the public API necessarily. It's this hook that's really just a closure that's defined in C++. And then whenever global tasks are enqueued onto the global executor, it's going to check that hook and call that first. And if nothing's overriding it, then it's actually going to use its default implementation. So with Swift, you can leverage DLSim and hook into this by telling it the name of the symbol that you want to map to and the exact type signature that it's defined with. That way, whenever you're referencing this variable that was defined with DLSim, you're actually directly accessing the internal of your library. That means you can override things. Maybe you can reference some constants that weren't re-exported that are sometimes helpful. So in this case, whenever we're enqueuing something on the global executor, we're actually going through our hook first. And if this looks familiar, it's because Brandon and Steven from the Point Free folks have covered this in their video series, and they use this in the composable architecture for more reliable and consistent testing. Episode 240, if you want to check that out. Why would you want to do this? Now, this is just one example of accessing your library's internals, but there's a whole category of use cases where sometimes the library author hasn't fully thought through all of the use cases. Maybe there's a bug that you're trying to work around, so you can reach into your dependencies to fix or augment them. Why would you not do this? Well, this is not type safe at all. Not only is it not type safe, it could go away at any point. It's also not part of the API contract, which means that whoever wrote this internal might be free to rename it, or maybe at some point the linker is going to strip it away when it's linking it into your application. And so you have to be mindful of all these things. And so use this judiciously, but nonetheless, it's a really useful pattern when you need it. Another fun thing you can do with the LSIM is you can defer loading of your untrusted third-party libraries. Why would you want to do this? Well, some of you may recall 2020 when apps all around the world just started crashing on launch. The truth is that whenever you're importing or linking a third-party library, especially if it's closed source and you can't necessarily see what's happening under the hood, it can run code without you ever even calling into it. And this is kind of sneaky. So how does this work? Well, if you want to prevent third-party code from running implicit things whenever you're just launching your app, not even calling into it, there's a few techniques that you can use, and some of them involve DLSIM. So instead of linking your library directly with your application, you can either weak link it or not link it at all and just embed it in your app's bundle. And then to think of this like if you were just adding any sort of image asset or a PDF or a font or something like that. You're usually not linking those to your application. They just ship alongside your app bundle. But it's not a font. It's a code-signed executable. You just don't happen to load it right when your app is launching. And by doing that, your third-party SDK is just living alongside your app. But then at that point, you get into a few problems. You can't just import the library. You can't just call into it normally, because at that point, the compiler doesn't even know you're using it. So how do you solve these things? That's where you can look into DLSIM. You can also take the same approach that we just saw with the Swift Global Executor hook earlier and use CodeGen to go and generate similar accessors to everything that was otherwise in the public API, so you can still access things in a type-safe way outside of that interface. You can also use the Objective-C runtime. Once you've called DL-open, loading your third-party library, at that point, that loads the Objective-C runtime classes. You can call into things. You can use your framework. Alternatively, you can use weak linking, and hat tip to my colleague at Ramp, Kabir, who suggested this, where if you rename the framework to something else, it's not going to eagerly link it when your app's launching. You can then just call DL-open on the renamed binary, and then at that point, it's just going to resolve all the symbols. So why would you want to do this? Well, sometimes you want to prevent your untrusted third-party code from running. Sometimes you don't know what it does. Sometimes you don't fully trust it. Some third-party libraries do really sketchy things. And ultimately, this is another use case of not letting your dependencies control you. You don't want something that your dependency is doing to crash all users of your app for something that they may not all be using. Why would you not want to do this? Many reasons. It can increase your distribution size if you're switching from static libraries to dynamic libraries, where the linker can't help you by shrinking it down to just the parts that you need, because at that point you're decoupling it. The compiler doesn't even know you're using it. It's kind of a lot of work. Who's got time for that? But nonetheless, it is a useful pattern. It's something that we've used in production at some of my previous companies as well to make sure that whatever third-party code we were using wasn't going to bring down the whole app for a very fixed set of use cases. Now, taking this approach, this pattern, even further, one of the things that you can do, if you're deferring loading that third-party dependency, what if you could also just choose dynamically what version of that dependency that you want to use? So let me give you an example, and this is taken straight from one of my projects called SourceKitten, which is a command line utility that will use SourceKit as it's installed on your machine and as is selected with Xcode select or developer dir environment variable. So effectively, don't necessarily try to understand all this code, but the part at the top is just a wrapper for DL open and DL sim. And the part at the bottom is iterating over paths where this binary might live. And usually what we're doing, especially in the SourceKitten case, is that we're matching exactly however xcrun would try to determine what version of Xcode, what version of the Xcode toolchain you have installed, so that we get to match that functionality. At that point, we load up the same version of libclang or SourceKit. Let's go forward instead of backwards. And generate, codegen, all of these accessors so that we can still access in a type-safe way those libraries' APIs, even though we didn't ship this library with our tool. In fact, that's kind of the opposite of what we want to do. We want to leverage the version of it that you already have installed and configured on your computer. So don't necessarily try to understand this code. Just get the sense that we are code-generating type-safe accessors to all of the APIs that we might want to be using. And again, this is an example that you can apply not just to a command line tool that I'm explaining here, but also if you want to publish an app on the store and you want to A/B test a third-party library where you really want to be sure that you're not regressing anything. Well, you can ship both versions of it, not worry about duplicate symbol errors, and choose which one you're using at runtime. So you could be using like a phased distribution approach for this third-party library that you're pulling in. So you can dynamically choose your dependencies by taking this. You can A/B test 2 different versions of a dependency. For Mac and command line apps, you can use a dependency that your users already have. And if you do that, you can reduce the distribution size because you're not bundling all your dependencies. You're leveraging some of the ones that your users may have installed. And by doing it this way as well, by not eagerly linking, you can avoid some duplicate symbol conflicts that would prevent you from shipping 2 versions of a dependency otherwise. Now, just like it can reduce the distribution size, this can also increase your distribution size. For example, if you're not using a dependency that your users already have, if you're shipping your iOS app and you're bundling 2 versions of your dependency so that you can A/B test between them, you have to ship those twice. And they need to be dynamic libraries because you're going to be loading them dynamically. It's kind of a lot of work. You need to build this into your build system. All this is possible, but you sort of have to have a very good reason why you want to do this. Nonetheless, it's kind of a useful pattern when you need to reach for it, and nothing else will really do the trick, because this isn't really part of the standard common iOS development toolset. Next up, our third cast member is Tilda Swinton with an epic suit. Love it. To show us a refactoring trick. This is leveraging one of the underscored attributes in Swift called _SPI. SPI stands for System Programmatic Interface. And one of the things that you can do using this is whenever you want to refactor an API and you want to step-by-step migrate all of your use cases, say you have a soup module and an old API to make soup, but you have a new and better way to make your soup. And over time, you want to slowly deprecate your make soup API. Well, you can mark it as @deprecated, but again, you're just going to litter your entire code base with warnings, and you're going to be forced to migrate either everything all at once or live with warnings in your code base. One of the things that you can do is annotate this with an @SPI and use whatever random identifier you want to put in there. In this case, I'm migrating the soup API, so I'm using soup migration. And at that point, at your call sites, you can import whatever module you've annotated with this with the same way to make that symbol available again. And there's another type of pattern that's useful for @SPI in a similar vein, and that's if you want to see everywhere in a code base that's using a symbol. Like in this case, I'm searching for the pitch keyword here, but if I do a text-based search, it's in all sorts of places in the code base. That word's used everywhere. It's a very common word. But if I want to know exactly what all the use cases are, I can annotate it with @spi, and at that point, the compiler tells me exactly where it's used. Right? So that's really helpful. Then I can sort of mark this one as @spi import, move on, see if there's any other ones that I need to be aware of. In this case, that was the only one. But in this case, it was a really helpful tool to help me find all of the uses of this symbol everywhere in the app. Finally, our fourth and final cast member, we have Bill Murray, who will show us, oh yes, Bill Murray fans, who will show us what we can do for testing. This is a pattern that I've seen in a handful of projects, is using domain-specific languages for testing and for things beyond testing too. Right? And the key thing that I want to impart on you here is that your tests don't always have to be written in the tests/something.swift folder of your Swift package dependency. They can be used for many other reasons if you can find a common way to represent them. So here's one case of using DSLs for testing that lives out there in the wild. The Swift async algorithms package published by Apple uses this string-based DSL to notate what the input should be, what the transformation on that input should be, and what the output should be. And what this is modeling here is values over time and how the transformation in the middle should be transforming it by using strings as a DSL and a representation here. So this is helpful because these strings, not only are they useful for tests, they can also be useful for documentation. This is another example, another Swift or another Apple package, Swift syntax, and they use emojis. Like in this case, on the second line, the one emoji indicates where they expect a marker to be used for the rest of the test. And so this, again, is like an expressive way to highlight what is being tested and what the input and output structure is actually supposed to be. Finally, this is a pattern that we use in SwiftLint, which is one of the projects that I'm involved with, where our tests are generally not written in the test directory of the package. They're in line whenever we're defining lint rules. So in this case, we have an example that highlights a bit of Swift code and a little arrow indicator that is embedded in the string literal that says this piece of Swift code should trigger a linter violation exactly at this position. Right? So in this case, we are modeling an example for a rule that is saying, well, instead of reducing, using the reduce and passing in a type, there's an often more efficient way to use reduce, which is reduce into a mutating variable. And so in this case, the linter rule will flag a usage of the type that we're trying to discourage and hint the user that they can move to something else. So I'll give you an example. In this case, I'm running SwiftLint's rule for the reduce inter rule. And if I move the arrow and run the test again, even though this isn't defined in tests, it's defined in the definition for the rule, we're going to get a test failure here because our tests are pulling from this value and iterating over them. And what's useful about doing things in this way is that you can reuse this DSL for reasons beyond just testing. You can also reuse it to generate HTML documentation. You can also reuse this approach for CLI usage instructions. Like in this case, we're getting the rule info for the reduce into rule, and we're getting all the same data. Right? So this is a pattern that I found very useful in some projects, which is to use DSLs sometimes for testing, but also for just general purposes. And finally, we have a final point that I want to showcase, useful pattern in testing, and that's leveraging external data sets in your testing. And generally speaking, this is something that's often discouraged, where you want your tests to be entirely self-contained and hermetic so that your tests pass 100% of the time and you have full control over them. And that is certainly a laudable goal. However, there's sometimes a lot of value that you can get if your tool or your function or your API is transforming data in, data out, where you can pull a data set from online somewhere and operate on that. One example, again, keeping in the theme of the SwiftLint project, is whenever someone makes a pull request towards SwiftLint, we will build the version of SwiftLint that their branch came out of, usually that's just the tip of main, and the version from their pull request branch. We'll build both of those versions. We'll pull a bunch of Swift projects from the internet, and then we'll run the main version of the tool, and then finally we'll run the changed version of the tool from the PR. And what this allows us to do is, doesn't really matter how often these external projects are changing, because all we'll be doing is diffing the result from the main version before the PR and the changed version after the PR. So to highlight a few things, one of the things that this allows us to do is if you're making a change to the tool, you can see, oh, this new version in the PR is introducing a new rule violation in this project. And this is doing that by scanning hundreds of thousands of lines of Swift code in all sorts of projects over the internet. You can also do performance testing if you're doing this, where you can compare the performance before the PR, performance after the PR, maybe cut out some outliers. And all of this is pretty straightforward, where it's about 100 lines of Ruby code that sets this up and basically pulls all of your external data sets, runs the version before, runs the version after, sees what differences there are, and can report it. In this case, we're using the danger tool. But this is a pattern that is applicable beyond just SwiftLint or even other tools that operate on Swift source code. If you're working on some sort of complex geopositional API and you can pull some geo data set from the internet, you can run your entire suite before your change, after your change, diff the results, see what's changed. If you're writing something that processes natural language, maybe you have some external data set that you can process before, after, run performance tests. So in general, leveraging external data sets is a helpful pattern. And in fact, the typical reason why you would not want to do this is because you don't control these external dependencies. But if you snapshot them so that you're running your before tests and your after tests with a fixed version, really you're just measuring the delta of your own tool. And so generally speaking, you end up getting a lot of value out of this practice without having to check in hundreds of thousands of external fixtures. So to recap some of the patterns that we saw, under the generics umbrella with Timothy, we had trampolines. Trampolines were useful for hooking into external APIs that maybe aren't dynamically hookable. You had warning traps where you can hide your warnings behind a protocol conformance. The DLSim tool helped us access the internals of our libraries to augment them and fix them. We could use deferred loading of external dependencies to minimize the risk of third parties that we don't necessarily trust when we pull them in our app. Using that same technique, you can then dynamically choose what dependency you're using at runtime. For refactoring, we had the SPI tool, which is pretty handy. For testing, we had the ability to leverage domain-specific languages and the ability to reference external data sets. And for closing thoughts here, I've got a nice quote from Bill Murray, which I think really helps us put all of this in perspective, really. Whenever we're thinking of the patterns we're using in our code or the architecture that we're applying, ultimately, Bill Murray says this: my iPhone has 2 million times the storage of the Apollo 1969-11 computer. They went to the moon, and I throw birds at pig houses. Right? Ultimately, these are patterns. These are tools to help us do our job, and we can't lose sight of that. There's another Bill Murray quote, and this has nothing to do with the talk, but I think it's good. Whatever you do, always give 100% unless you're donating blood. By the way, I work at RAMP along with Kabir, who's another speaker. We are hiring for some engineering roles, so if you're interested in joining us and working with us, take a look. Thank you.